Hi everybody, this is Matt Morgan. In this lesson we're going to talk about types of intermolecular forces from Wiley's section 11-2. So in this lesson we'll review intermolecular forces, then we'll talk about the types of intermolecular forces: London, dipole-dipole, and the important subset of dipole-dipole hydrogen bonding. In the course of this lesson we'll also work Wiley problem 11-07. So intermolecular forces are attractions that exist between different molecules. Properties such as melting point, boiling point, and surface tension depend on the magnitude of intermolecular forces. The first type of intermolecular force that Wiley talks about is the London force. It's also called dispersion forces. London forces are the weakest of the intermolecular forces, and London forces exist between all molecules. It's the primary intermolecular force between nonpolar molecules, and we talked about nonpolar molecules in a previous lesson. So how can we have an intermolecular force if there's no electrical charge between two molecules? Well, electrons in an atom or a molecule are not in a fixed position. They're constantly moving. In fact, we learned earlier in the course that they behave like waves. At some instant, these electrons will not be evenly distributed around the atom or the molecule. The moment that the electrons are uneven, you have a dipole, an instantaneous dipole. And this weak dipole can cause uneven electron distribution in nearby molecules. This is a very weak attraction. The London forces are the weakest of the forces. The boiling points of molecules attracted only by London forces are very low. Let's see how a London force is caused. If we have a neon atom with its 10 electrons, at some instant the electrons may be unevenly distributed. In this picture we have more electrons on the right hand side of the atom than the left. That little squiggle means that we have developed a partial negative charge on the right hand side, a partial positive charge on the left. That's a small Greek letter delta. If another neon atom approaches, that small negative charge will attract the positive end of other neon atoms. So we get a very weak intermolecular force, a weak attraction between these two atoms. Now we know this is very, very weak because the boiling points are low. We'll see that on the next slide. This animation shows the London forces in action. Look at the electrons unevenly distributed. The partial negative on one side is attracted to a partial positive on another. So here are our boiling points. 4 degrees Kelvin for helium, 27 degrees Kelvin for neon. It's difficult to visualize the Kelvin scale. Let's convert those to Fahrenheit. Minus 452 degrees. That's really, really cold. The attraction is very slight, so they boil at a low temperature. You don't have to memorize these, but just realize that they are low temperatures and look at the trend. As we go down the periodic table, the boiling points increase. Let's talk about that. So as you move down the periodic table, the atomic number increases. But it's not the atomic number that determines the boiling point, it's the number of electrons. The more electrons you have around a molecule or around an atom, in the case of the noble gases, we get a stronger London force. If we want to rank the strength of London forces, let's use the molecular weight, because molecular weight will also tell us the number of electrons. So let's do a Wiley homework problem that has us order materials based on their London forces. That's 11-07. So we want to rank order the following an increasing magnitude of London forces. That means we're going to start with the smallest and then go to the biggest. So we said that larger molar mass is larger London force. Let's find the molar masses of all of these items. There's one atom and 3 molecules. Okay, xenon, I look at the periodic table, 131.29. I calculate the molar mass for all the rest, and there are my molar masses. So we order these from smallest to largest, smallest being the methane, followed by nitrogen monoxide, xenon, and finally the carbon tetrachloride. There is our smallest to largest ordering. The actual question has you use drop downs, so we look at that. We see that our carbon tetrachloride, our methane, number 1, nitrogen monoxide, number 2, xenon 3, carbon tetrachloride, number 4. And that's correct. So the next intermolecular force is the dipole-dipole interaction. They are stronger than the London forces. Materials that are attracted by dipole-dipole have higher boiling points than materials only attracted by London. And dipole-dipole forces exist between 2 polar molecules. The partial positive side of one is attracted to the partial negative side of another. Here's a very simple diagram. Negative and positive attracted to each other. A lot of chemistry is explained by that phenomenon. So a stronger dipole and a smaller size makes for a stronger intermolecular force. In the previous lesson we talked about Coulomb's law. So a special type of dipole interaction is called the hydrogen bond. So hydrogen bond exists between molecules that contain hydrogen, hence the name, but bonded to nitrogen, oxygen, or fluorine. Now the hydrogen bond is a specially strong type of dipole-dipole interaction. The hydrogen bonds are stronger because nitrogen, oxygen, and fluorine are very electronegative, giving us a large dipole. They are also very small, and the molecules can get close to each other. Strong dipole, small size, makes for a strong intermolecular force. Water is a very common molecule that experiences hydrogen bonding. Here's a diagram. We see the covalent bonds between the hydrogen and oxygen, but hydrogen bonds exist between the partially positive hydrogen side and the partially negative oxygen side of these water molecules. Here's an animation showing hydrogen bonds. So here's a big takeaway. Hydrogen bonds are a special and stronger example of a dipole-dipole interaction. So we talked about 2 types of intermolecular forces, the London force, dipole-dipole interaction, and its subset hydrogen bonding. We showed how London forces vary with molecular weight. We worked the Wiley problem. As always, contact your course mentors if you have any questions. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.